Hello everyone. So we're going to continue electric fields. You already know that if there's a point charge, let's say a positive charge as shown in this PowerPoint slide to the left, we say that the electric field pointing, extending outwards, symmetrically extending outwards from the charge. So we represent it by lines with arrows pointing outwards. If it is a negative charge like an electron, we say that electric field pointing inwards. So these lines are called electric field lines. It's a graphical representation to show how the electric field looks like around the charge. It's a convenient way to represent the shape of the electric field. So we'll look into that, couple of different shapes of charges. So let's see what's next. So number of lines tells us about the strength of the electric field. So for an example, let's say you can say here's a positive charge, so here's electric field going out from it. Okay, alright, now closer to the charge, let's take some area closer to the charge, let's say this area. This area has 3 field lines going through it. If I move the area and draw the same size over here, it pretty much covers only one electric field line. So the number of electric field lines tells us that it's much stronger. More field lines in an area, the field is stronger. Less field lines, the field is weaker. So this is a good way of explaining the shape, the strength and all that. Okay, so these are simple things about electric field lines. What else we have? Electric dipoles, or two opposite charges. So let's learn how to draw field lines between charges, right? So if you have a positive charge and a negative charge, the electric field between them, the positive one extending outwards, negative one coming into it. When two charges next to each other, positive and negative, what happens is the electric field going out from the positive charge goes into the negative charge. So it's going to appear like this. These charges are also bending in such a way that after completing a long circle, they might come back and appear here. So the electric field between two spherical charges is going to look like this. It's much stronger in between and getting weaker as you go away from it. Alright? Okay, so before going to this, let's try another one. What if we have two positive charges? What is the electric field between these two going to look like? So electric field has to go away from the positive charge. Same with this positive guy, they have to go away from the positive charge. So in between, they actually move away from each other. They are repelling, these field lines are repelling each other. Okay, so we talk about this in class. When we do calculations, if there's two charges, in the middle there's a void. There's no electric field in the middle because the electric field kind of try to cancel out each other. You can show the same thing using these field line diagrams. Somewhere over here there is some electric field. See, they are all going in one direction. And right in between it's going to be a void. So this representation helps for us to understand the electric fields in a little graphical way. Alright. How about two negative charges? How do you draw that? Go ahead and give it a try. You can pause the video and try it yourself. It's gonna look like this. It's coming into the charge, so you're gonna draw it like this, coming into the charge like this. In between there's a void, right, between the two charges. Okay, all right. Two closely spaced, oppositely charged parallel plates. Again, we talk about this also in class, so let me clear this. When we have two parallel plates, it can be like a plate, like with an area like this. Right, so I'm trying to draw a 3D diagram. Here's a plate. You can place another plate over here. And if one is positive, so we place a lot of, like we remove a lot of electrons, make it positive. There's a lot of electrons on this. So it's going to create an electric field from the positive to negative. This is the plus Q, minus Q. We need to make them equally charged. Like if this is 10 coulombs, this will be minus 10 coulombs. If the numbers are different, it won't be that symmetric. There will be little bumps here and there. It's going to be a complicated pattern. So, or it could be two lines of charges, like a thin cylindrical conductor, kind of something, positively charged, negatively charged. Same thing, you have a strong electric field in the middle. Again, these things have so many good applications, which we will talk about them eventually. Let's see what else we have. So a summary of field lines. Field lines indicate the direction of the field. The field is tangent to the line. Its electric field goes with the line. The magnitude of the field is proportional to the density of the line. The more lines you have, number of lines, more lines you have, it tells you that it's a stronger electric field. Field lines start on a positive charge and end on a negative charge. The number is proportional to the magnitude of the charge. Okay. Alright, so that's about electric field lines. Alright, so let's move on. Electric fields and conductors. So, we talk about point charges. Like a little point charge like a proton or something, right? There's no dimensions. A negative charge, an electron, no dimensions. But when it comes to bigger objects, not these microscopic small tiny point particles, but actual bigger objects with some dimensions, like a solid sphere or some metallic cylinder, or it could be any like something made out of an insulated material, but we place some charges on it. Things act a little differently. There are some interesting things we can talk about them. So for an example, let's say we have a metal sphere, something made out of, for an example, iron. So this is a solid sphere, right? It's a 3D object. It's all iron inside. So if you let's say you want to charge it positively, means you are removing electrons. Okay, here's a different way to understand. Let's say you want to charge it negatively. So you are bringing in electrons into this. You put all the electrons on this thing. A lot of electrons on the surface and inside everywhere. Right, this is a metal sphere. So what happens is these electrons, so conductor, for an example, is a conductor. These electrons they have freedom to move around, and you know that like charges, equal charges, they try to repel each other as much as they can. So there's repulsion between them. They all try to take maximum distance away from each other. What happens is eventually means more like immediately, doesn't take much time, all these charges will take the maximum distance from each other, and they're all gonna be residing on the surface of the conductor. This happens only for conductors, right? There won't be any charges inside. They all try to go to the outer surface. It doesn't need to be a sphere. It can be a cylindrical object. You place some electrons. They're all gonna be residing on the outer surface. There won't be any charges inside. We will talk, we'll get into details about these things later. There's some interesting calculations we can do to find the electric fields of these kind of macro objects, not microscopic but macroscopic objects. But for the time being, if it is a conductor, you can't place charges inside. They immediately move around and resides on the outer surface. It doesn't matter if you try to introduce positive charges to something. Still, electron-proton recombinations will occur, and it will make sure that all the charges, positive charges, will appear on the surface. It's difficult to place charges and expect them to be there inside a conductor, right? Things are different if it is an insulator. Insulators, there's no much freedom for electrons to move around, things like wood or plastic, those kind of stuff. In these kind of things, let's say you have a wooden sphere, and you want to place some electrons, you want to charge it, so you have to introduce some electrons. You can place them wherever you want. They won't move, they won't have much freedom. So in an insulator, you can place charges on the surface, inside, wherever you want, right? So that's the main difference between conductors and insulators. Conductors, you can't have charges inside. They all come to the outer surface to get the maximum possible distance between them. Insulators, you can place them wherever you want. Alright? Okay, let's move on. Alright, here's another example of what we just discussed. Here we have two metal plates. You see that positively and negatively charged, and you place a hollow metal box, a metal box, but inside there's empty space. You place it in the middle. Now in the second diagram you see there's an electric field between the positive and negative. One interesting thing happens. So you have this electric field, and then you place this metal box inside. This is metal. Inside the box is empty space. So what happens is there's the electric charges like protons and electrons in this metal box, on the surface of the metal box. They're going to rearrange in some way that it's going to make sure that there is no electric field inside. The field inside the box disappears. So the electric field will look like this. Outside there's electric field, but there's a discontinuation inside the box. They come here and they appear from the other side and continue. Within the box, no field. This has to be a conducting one, right? Metal or conducting. This is called electric field shielding. The field is being shielded by this box. So it doesn't need to be a box. It can be any kind of metal space, covered space. A good example is when you go inside the elevator, sometimes you don't get much phone signal strength. These phone signals, at the end, the electric field come into your phone. You go inside an elevator, it's kind of acts like a metal cage, so it shields your phone from getting these signals. That's one example. Sometimes in some buildings, if it is like a warehouse kind of thing, like a metal structure, right, you might not get good reception inside. It's not because of there's no signal towers nearby. You've been shielded because of these metallic frames. This effect is called the Faraday cage effect. Michael Faraday actually did a lot of research into this. He lived probably like 200 years ago, I believe. Yeah, that time he didn't have cell phones or anything, but he realized that electric fields can be shielded and things inside the box are protected from these electric fields. Another good example is during thunderstorms, when there's lightning. You might have heard this, that being inside the car is safer. So here's the road, here's the car, and there's a lightning cloud, and there's lightning going on. So there's a person inside. Now, many people believe that you are safe inside the car because these rubber tires, these are insulators, so they will protect you from the lightning. If you're just standing outside, which you should not do during lightnings, you are the tallest. Let's say there's no trees or anything nearby, there's no tall buildings or anything nearby, so the lightning always look for the shortest path to the ground. So if you are the tallest, you have a higher chance of getting this lightning, and then it's going to go through you, which is really bad. Never try this, right? If there's trees around, let's say a tall tree, my diagrams are really bad, it's relatively better, you have a better chance because tree is the taller structure, so the lightning can go through this. But you should never stand underneath the tree, because these lightnings can branch out while going through the tree. If the tree trunk has more resistivity, it will look for the least resistive part. It will jump back from the tree and then go through the person. So the bottom line is, lightning look for the shortest, least resistive path. That's why we say that when there's thunderstorms going on, don't go outside, don't go into a playground. If you are in a playground, lie down and try to crawl back, don't walk. Okay, so let's go to an alley, something like that. Tall buildings have these lightning conductors, so lightning arresters, lightning repellers. These are like metal conductors that gives a safe path to the incoming lightning. Okay, coming back to the point, when there's lightnings going on, if you are inside the car, this acts like a metal shield. The car is a metallic body, so acts like a metal shield. So even if there's a lightning strike, it won't come inside, it will go around the body and get to the ground. These rubber tires, if it is raining, mostly it's going to be conducting. Rubber tires won't prevent you from getting the lightning, but it won't come inside the car, right? This metal cage will make sure that there's no electric field coming inside. Same way that when there's lightning, let's say you are inside an aeroplane, there's lightning, this electric field can go around it and get out, but it won't come inside because this is made out of metal, so relatively safer. I wouldn't say that it is absolutely safe, but relatively safer. Okay, So if you are interested, please read up more about these things. There's a ton of information. Lightning sciences are pretty interesting. There is some research I have seen some time back about growing special kind of trees to prevent lightning. Like these certain shapes of leaves can kind of acts like, lightning repellers. There's a lot of interesting things going on in this field. Okay, let's see what's next. Alright, so the next topic I want to discuss is motion of a charged particle in an electric field. So let's do some math. This is an interesting topic. Alright, let's clear this. Let's say you have two charge plates, oppositely charged plates, positive plate and a negative plate. Now you know the electric field between them from positive to negative. It's going to be a strong, uniform, parallel electric field. Alright. Now if you, let's say, release a proton here, a positive charge, it's going to get the repulsive force from the positive side and attraction from the negative side. Also, you know that the electric field, the same thing applies a force in the same direction, so there's a force on this. So if you release a proton here, it's going to get accelerate. Now there's a force acting on this thing, right? Let's forget about the gravity for the time being. Comparatively, when it comes to these kind of very small particles like protons and electrons, electric force, right, force due to electricity is much greater than force due to gravity. Yes, this proton get pulled by the gravity downward, so it's not like a completely horizontal path. It will be like something like this, but that's very minimum. Right, gravitational force is really comparably, later we can do some math and show that, very small. So what happens here is, so let me erase all these things. There is a force on this proton. It's going to get accelerated towards the negative side. Or if you have an electric field like this and you place an electron here, negative charge, it will accelerate in the opposite direction. Now these accelerations are very important because there are so many applications in science, not just physics, but in science, in biological sciences, medical research and all that, to accelerate particles and to use them for certain purposes. In physics, like a good example is all these big physics, like nuclear physics labs, where they accelerate these particles. Like think about the Large Hadron Collider in Geneva, LHC. They accelerate particles and smash them against each other, smash them into other targets, other molecules, to study what's inside. Why do you smash them? Because, like, why do we need so much high speeds? Why do you need to accelerate them into very high speeds? Imagine you want to study the nucleus of something, like, okay, some big molecule, let's say gold, right? So there's a lot of protons in the nucleus. Everybody knows about gold a lot, but let's say there's some exotic material we want to study. So how do we see inside the nucleus? We can't. There is no probe that can go inside, right? And there's electrons around it. Acts like an electron cloud. So one technique is actually to have very high speed atoms, protons or neutrons, not really neutrons, but protons or electrons. You have to have charged particles. You can't accelerate neutrons using an electric field, but these two can. So you accelerate them, give them a very high speed, aim them towards the nucleus. So you isolate atoms and then you have this beam of protons coming in. They will go, because of this very high speed, they are able to go through this electron cloud without getting attracted by them, go inside the nucleus and sometimes break the nucleus or knock some of the protons out, knock some of the neutrons out. In these reactions, by observing what happens, like how much energy it's going to release, what kind of momentum these protons that are coming out will have, what kind of spin they will have, we can learn a lot about what's going on inside. So that's why these, and to do that you have to have very high kinetic energies, very high speeds. So that's why these accelerators are so huge. There's different techniques of accelerating them. There's magnetic methods, there's electric field methods, there's combinations of both. This is a very, electric fields are very simple, straightforward technique, mostly used in smaller size accelerators, I would say like medical level accelerators. But yeah, this is the principle behind it. Okay, so let's try an example. Okay, so this example says electron accelerated by an electric field. So here in the PowerPoint slide you see that there's two metal plates creating an electric field. It's pointing to the left. You place the electron close to the negative side and you release it. We know that the force is in the opposite direction. And actually there's a little cavity on the positive side where this incoming electron can come out, and then we can use it for any useful procedure. So the separation of the, okay, let me erase all this. Alright, so you guys go ahead and try this first, pause the video, give it a try by yourself, and then come back and check the video. Okay. So electric field is pointing in this direction. The distance is 1.5 cm, gap between them. You release the electron right here. With what speed does it leave the hole? Show that the gravitational force can be ignored. Okay. Alright. So when you release the electron from here, there's a force acting on it, a uniform force, which can be calculated. F equals QE. It's an electron, so it's 1.6 10 to the negative 19. You don't need to put the negative sign, right? The negative sign gives you the direction in this case, so we know which way it's going, so don't worry about that. Multiply by the electric field is 2 times 10 to the 4, so that gives you 3.2 times 10 to the negative 15 newtons. That's the force. So the electron is under this force. Now what is this force is doing? It's going to accelerate the electron. So let's find the acceleration of the electron. We can use F equals ma. So the force is 3.2 10 to the negative 15. Mass of the electron is given 9.11 10 to the negative 31 kilograms times acceleration. So acceleration, divide one by the other. Right, need the calculator for that. 3.2 divided by 9.11, 0.35. 10 to the 15 divided by 10 to the 31 is more like 10 to the 31 is the positive one, so 10 to the 16 can be written as 3.5 10 to the 15 meters per second squared. A very high acceleration. extremely high acceleration. It travels a short distance. Now, if it travels a longer distance and reach speeds more than, if it is getting close to the speed of light, we know that we can't go above speed of light for these kind of things. Then we have to switch to relativistic equations, which we're not going to do. So we're going to keep our examples below the relativistic limits. All right. That means if you see the answer is going to be more than speed of light, that means you're not doing it right. That means you have to switch to relativistic equations. In this example, hopefully, it won't go that far. Okay, so we have the acceleration. How do we find the speed when it comes out at this point? What's the velocity? Go back to the kinematic equations. V initial starting from 0, V final is what we are looking for. The distance it travels is 1.5 centimeters. And the acceleration is, we just calculated. So, yeah, we can do this. V final squared equals V initial squared plus 2ax. 2 times 3.5 times 10 to the 15 times 1.5 times 10 to the negative 2. 3 point, am I doing this right? I think I'm doing it right. 3.5 times, so 10, something close to 1, 10, 3.5 times 2 times 1.5, 10.5, 10 to the negative positive 13. This is V final squared. Positive 13. V final is the square root of that. How do I get the square root? I'm going to do a little trick here. I'm going to write it as 105 times 10 to the 12. I'm going to move this decimal point once, and I will use one of the tens for that. Now I can square root, right? V final is this, so the V final is square root of this. So I move this. Now I need to find the square root of 105. So square root 105 10.2 times this becomes 10 to the 6 meters per second. So finally I have 1.02 times 10 to the 7 meters per second. That's the speed. It's an extremely high speed, 10 to the 7 meters per second. One order above is the speed of light. Speed of light, you might know this, approximately 3 times 10 to the 8 meters per second, right? If you get an answer close to this or above this, that means it's more like you're not doing it right. You have to switch to relativistic calculations. We won't do those in class. Okay, so going back to this. This is how we accelerate charged particles. We create these uniform electric fields and we place charges. Based on the charge, it creates a force. That force creates acceleration. That force you calculated, it's what goes here. And that gives you the acceleration. With acceleration, you can find the final speed. You can even find how long it takes to go from one place to the other. It's like a fraction of a second, right? Part 2 says compare this to the gravitational force. Well, the force on this electron is this. What's the gravitational force acting on the electron? Gravitational force, or in other words, its weight. If gravity is W is mg. So 9 times 10 to the negative 9.11. 9.11 times 10 to the negative 31 times 9.81. Really doesn't do much. This is more like again 9 times 10 to the negative 30 newtons. Compare this. 10 to the 15 times smaller, right? Really, there's no comparable effect from the gravity in this case. Okay, so let's move on, and we will work on a couple of examples like this. Here's another interesting one. So say that this electron comes out from this cavity over here. So I'm gonna so we have the speed. Okay, we already have the speed, so I'm gonna erase this. Actually, I can erase the whole thing. So here we have the cavity, the accelerator with the electric field. Now the electron comes out. Electron comes out with a speed of 1 times 10 to the 7 meters per second. Once it comes out, what they do here is now they try to deflect it. So here we have another arrangement. This time we have a negative plate up here and a positive plate down here. Please pardon the noise. My doggies, they don't want anybody to walk around the neighborhood. You guys know that. So we have this second electric field. This is to deflect the electron. Now this electron is coming perpendicular to that, right? The electric field is pointing this way. So it's coming in. It feels a force perpendicular to its direction. It's moving this way, and it's feeling a force perpendicular to that. So it's gonna pull. While it's moving to the right, it's gonna get pulled vertically downwards, so eventually it will go in a path like this. Now these deflecting techniques are also very important. This is to the first part. These plates are to accelerate. These plates are to guide. Guidance systems. You create a fast beam of electrons. Now you need to apply them into the targeted cancer cell or something like that. You need to hit the target. So you have this guidance system. By changing the electric field, if you want to deflect it upwards, you make this side positive and this side negative. It's going to deflect upward. By changing the strength of the electric field, you can guide them to the angle you want, right? So there will be questions like, all right, how much electric field I need to deflect it by 2 centimeters. So we will work on these kind of problems later. Okay, so math-wise, that's all, and then let's look into some few interesting applications, some other things. For an example, in biology. You guys, most of you are biology students, so you must be wondering where to apply all these things. Well, a good application is, well, I'm not an expert by any means on these kind of things. I just read in the textbook, DNA molecule, the distance between the two strands is super important for it to function properly. So these distances, this fine distance, this like nanometer level distance, is governed by the electric field or electric forces. So either side there's molecules. These molecules have charges. Some are charged ions. They have these electric fields between them. So they make sure that this molecule, this DNA thing, always have that proper size. What else? And I don't know what these things are, but it says the A and T and G and C always reconnect, combine because of the respective electrostatic forces. Okay, means electric charges and the forces due to electric charges. So so that's that. Let's see what else. Yep, a little bit more about DNA. And finally, I want to talk about another thing, electric dipole. When you have two opposite charges at a fixed distance, a positive charge and a negative charge at a fixed distance in a molecule, not a good diagram, plus and minus, we call it an electric dipole. And dipoles have interesting properties. Let's say there's an electric field and you place a dipole in this. So a molecule it won't look like this, it will be more like this, plus and minus. Now there is no net force on this thing because the charges are equal. The positive feels a force this way, but negative feels a force in the opposite direction. So this thing is not going to move. But we redraw this. If you place this thing at an angle, plus and minus, here's a force, gives it a rotation. So dipole molecules, a good example is H2O, right? Oxygen and the two hydrogens. Oxygen is negative, the hydrogens are positive, so it kinda looks like, it's a bad diagram, the two hydrogens here, it's kinda more positive side and a more negative area. So this is a dipole molecule. H2O is a famous dipole example. So molecular recombinations, the rotations, how they align in liquid water versus in ice, all these things have a lot of influence because of this dipole property, right? So that's a common example, just for your knowledge. We're not going to do any math with these things. Okay, what else? Alright, so I think that will be enough for the day. I went over the time limit. I wanted to keep it under 30. It's 42 already. We are mostly done for the electric fields. University physics class, you guys will have probably another short additional video coming your way. And we'll discuss some problems Wednesday and Friday in the coming days. Okay then. Thank you everyone.